Let's jump right into this explainer. If you've ever wanted to truly understand how software directly manipulates the physical world, well, you are in exactly the right place. Today, we're doing a whiteboard-style deep dive into assembly code. We're not just going to talk about abstract concepts here. We are going to map raw, low-level commands straight to physical hardware actions. We'll trace the whole journey, from simply blinking a light to actually teaching a microchip to, think and react. Now, to really grasp assembly, we absolutely have to ground ourselves in the physical hardware. Take a look at this schematic. Right there in the center, that's our brain, the PIC16F84A microcontroller. And notice exactly how the real world connects to it. We've got a push-button switch tied to pin 2 over on the left, and an LED connected through a resistor to pin 13 on the right. When we're writing assembly code, we aren't just typing words on a screen. We are literally manipulating the voltages on those specific physical pins to make that LED flash or to sense if someone actually pressed that button. Here's our roadmap for today's explainer. 1. Lighting up the hardware. 2. Mastering time with delays. 3. Building reusable subroutines. 4. Reading physical inputs. And 5. Advanced bit manipulation logic. Kicking things off with Section 1, lighting up the hardware. Bits to volts. Our very first goal here is simple but totally foundational, making the microcontroller blindly turn on an LED. Now, we can't just yell turn on at the chip, right? We have to follow a strict initialization sequence to physically configure the pin. Let's walk through the code. Step 1, we use BSF status, 5 to select memory bank 1. Why? Because that's where the configuration registers live. Step 2, we use BCF trisb, 7. The trisb register controls data direction, and by clearing bit 7 to a 0, we are physically configuring pin RB7 as an output. Step 3, we use BCF status 2, 5 to hop back to memory bank 0. Only after all that setup can we finally use BSF port B, 7 in our main loop to actually pull that pin high and turn the LED on. But you know what's really fascinating? It's what exactly happened inside the chip when we typed BSF status, 5. Point your eyes directly to bit 5 on the status register map. It's labeled RP0. The command BSF stands for bit set file. When we ran that, we reached directly into the chip's memory architecture and flipped that single RP0 bit from a 0 to a 1. That microscopic flip is the literal physical switch that changes our active memory bank from bank 0 to bank 1. It's just a perfect example of software directly altering hardware state. Moving on to Section 2, mastering time with delays, the speed limit. So once we get the LED on, we immediately run into a huge issue. Microcontrollers process commands so incredibly fast that if we turn an LED on and off sequentially, human eyes won't even register the flicker. We need artificial speed limits. Which brings up a critical question. What happens when our microcontroller is driven by a 32 kHz crystal oscillator? Well, we could try to stall the processor by having it count down from a maximum value. But even if we stuff a counter register with its absolute maximum hex value of FF, counting that all the way down to 0 at 32 kHz only creates a microscopic delay of about 93 milliseconds. To you and me, that's still just a flicker. To fix this, we rely on a true workhorse, assembly command, DCFSZ. That stands for Decrement File Register, Skip Next Instruction if 0. This brilliant little command lets us build software delay loops. We constantly count down a register and check the result. Not 0, we loop back. Is it 0? It skips the loop instruction and moves right along. And this shows exactly how we bust through that 93 millisecond limit. We nest these DEFC's loops inside one another. Check out this structure. We have an inner loop that counts down, and an outer loop that triggers the inner loop again and again. By embedding loop 1 inside loop 2, we are mathematically multiplying that tiny delay. It's kind of like the minute hand and the hour hand on a clock, working together to create a highly visible human-scale pause of several seconds. Pretty cool, right? All right, Section 3, building reusable subroutines. Working smarter. Okay, so we've solved the delay problem, but now our code is getting a bit messy. If we want the LED to turn on, wait, turn off, and wait again, copying and pasting that nested loop over and over makes our code incredibly bloated and super hard to read. Just look at the comparison here. The old way means manually injecting lines and lines of DCFZ commands everywhere we want to pause. The new way, it shows the brilliant simplicity of working smarter. We literally just take that entire nested loop block, move it to the very end of our program as a standalone subroutine. Now, whenever we need a pause, we simply trigger it with the call delay command. The processor jumps down, executes the delay, and hits a return command, which elegantly bounces it right back to where it left off in the main program. Which brings us to Section 4, reading physical inputs, listening to the world. Up to this point, our microcontroller has been completely deaf, blindly flashing based on a timer. It's time to teach the hardware to actively listen for human interaction from that button on pin 2. We do this by creating what's called a polling loop. The microcontroller repeatedly reads the binary voltage of pin RA3, just waiting for a user to press the physical button. Here is the exact sequence. Step 1, we read the port. Step 2, we use a command called BTSS to test bit 3. Step 3, if the bit is set, meaning the button is actually pressed, we skip the next instruction and proceed to flash the LED. Step 4, if the button is not pressed, we simply loop right back to the beginning and read it again. It's essentially the chip constantly asking, "Are you pressed yet? How about now? Are you pressed yet?" So the really crucial part here is how we actually perform that read operation. Look closely at this command, move F port A, 1. This is such a fascinating assembly trick. We're telling the chip to read the contents of port A and move it right back into port A. Setting the destination to 1 means the file register itself. Now, why on earth would we do something so seemingly redundant? Because the very act of moving data through the processor updates the status flags, specifically the 0 flag. By doing this seemingly empty move, we guarantee the internal flags are perfectly updated right before we execute BTSS port A, 3 to test the bit. Moving into our final part, Section 5. Advanced bit manipulation logic, surgical precision. So we know how to turn a single pin on or off, but what if we need surgical precision to configure multiple pins simultaneously? Changing a single bit is easy, but if you need to change, say, bits 2, 4, and 6, all at exactly the same time to coordinate a complex output, writing repeated BCF and BSF commands is just highly inefficient. It wastes memory, it wastes processing cycles. The much more elegant solution is to use logical operators and/or an exclusive OR. Let's map this out clearly. This matrix shows exactly which logical operator we use for specific bit manipulation tasks. If your goal is to clear specific bits to 0 while leaving the rest completely alone, you use the AND operator, which in assembly is AND-WF. If you want to force specific bits to 1, you use the OR operator, which is IOR-WF. And if you want to check if 2 bytes are identical, you use the XOR, or exclusive OR operator, utilizing the XOR-LW command. Let's look at exactly how these work in practice. Here's an exact AND logic example. Imagine we have a register called motoreg, and we want to ensure bits 2, 4, and 6 become zeros, but we absolutely cannot alter the other bits. We create a mask. We move the binary value 1, 0, 1, 0, 1, 0, 1, 1 into our working register. Notice the zeros are precisely at positions 2, 4, and 6. When we execute AND-WF motoreg, 1, the logic rule states that anything ANDed with a 0 becomes 0, and anything ANDed with a 1 stays exactly as it was. Boom! We have surgically cleared our target bits in a single cycle. Now, let's see how this applies to the opposite approach. Suppose we want to force bits 2, 3, and 4 in a register named Reggie to become 1s. We use an inclusive OR operation. This time, our mask is 000111100. The logic rule for ORs states that anything ORed with a 1 becomes a 1, and anything ORed with a 0 remains unchanged. So, by executing IOR-WF, Reggie, 1, we instantly force those 3 middle bits high, beautifully modifying the Reggie register in one shot. And finally, maybe the most elegant trick of all, the exclusive OR. Say we need to check if a register perfectly matches a specific value, like 10101101. We use XOR-LW against that exact same binary string. The rule of XOR is that if 2 compared bits are identical, the result is 0. So if the whole byte matches perfectly, the entire result is 0. And remember our status register from earlier? A mathematical result of 0 instantly sets the 0 bit, which is bit 2, in the physical status register to a 1. We can then immediately follow up with a BTFSC or BTFS on status bit 2 to branch our code based on that match. It's a really neat trick. From blindly flipping a voltage high to turn on an LED, to carefully constructing infinite time loops, to using bitwise masks to surgically alter memory, this is the hidden language of machines. Which leaves us with this final thought. If every modern system, from your smartwatch to giant cloud servers, ultimately relies on these exact microscopic bit manipulations at its core, what physical hardware actions is the device you're watching this on secretly triggering right now? Keep asking questions, keep learning, and thanks for joining me on This Explainer.